Bam! Mr. Tarrou, in this math lesson, we're going to take a look at 3 examples of writing equations of planes using a normal vector. But we're first going to start off by trying to help you understand the geometry behind this new equation that we're going to learn, in addition to the 3 that we've already learned, which is the vector form for the equation of a plane, parametric form, and Cartesian form. Then we're going to move through these 3 examples, the first one of which is a released question from an old IB exam that kind of doesn't leave any option other than working with and understanding how this equation that we're about to develop works. Then we're going to do 2 more examples where we're going to be given, let's see here, find the equation of the plane if it contains 2 lines that are given in Cartesian form, and find the Cartesian equation of the plane if it contains a particular point and a line. Our last one is going to, or first one actually, our first example is going to be find the Cartesian equation of a plane pi containing a couple of points and is perpendicular to another plane. And that equation of that plane is going to be given in Cartesian form, which is what, kind of you really want to understand this new formula we're about to develop to be able to work through that problem. So we have this equation pi. We have an initial point that we're labeling with the coordinates, just like in the last video, of x sub 1, y sub 1, z sub 1, indicating that it is the one known point that we have on the plane. And then we have all of our other general points of r described, well, a described with the position vector a, and this any other point on the plane described with the position vector of r. And you're going to move from a to any other point on the plane through the addition of scalar multiples of our 2 non-collinear directional vectors, which may be in the plane or parallel to the plane. So again, just I'm over-explaining some of the stuff, I'm sure, but I don't know where you're coming from into my video lesson and what your background is and what kind of questions you have. But it's pretty cool that the equation of a plane, especially in vector form, is really just like that y equals mx plus b that we learned all the way back in Algebra 1. You have to have a fixed point, and then from that fixed point, some multiple of a gradient. And the vector u and vector v, those non-collinear parallel vectors, are acting as the sort of 2-dimensional gradient of this plane. Well, we're going to work with a normal vector. So, in other words, a perpendicular vector. And how do you take 2 vectors in 3-dimensional space and, well, the plane's 2-dimensional, but we're moving along the x, y, and z axis to find a point out in 3 space, and ultimately these vectors out in 3 space. You do a cross product, right? The cross product of vector u and v is going to result in some type of normal vector, which is going to be orthogonal to the 2 vectors. Orthogonal is just basically another word for perpendicular. Orthogonal to the 2 vectors which you ran through the cross product process. Now, we have this vector n, which is perpendicular to plane, in this case, pi. Now, if I look at a vector that starts at my initial point A and goes to, whoa, chalk down, goes to, oh, broke a lot, okay, goes to any other point that lies within the plane, we're going to have vector AR. Now, the only way that vector AR is orthogonal or perpendicular to vector n is if r is in the plane. So with that statement, we would then understand that the dot product is equal to 0. There's an algebraic definition for the dot product, which I'm going to use right now, or at least at some point very, very soon. And there's a sort of geometric definition of dot product or scalar product that says that the dot product between 2 vectors is the magnitude of one vector times the magnitude of the other vector times the cosine of the angle between those 2 vectors. And if the angle between those 2 vectors is 90 degrees, well, the cosine of 90 is 0. Thus, the dot product, scalar product, is equal to 0. We need to write out, in component form, vector AR. Well, that's going to be terminal minus initial. So we have x minus x sub 1, y minus y sub 1, z minus, you could write those minus signs big enough you could see it, z sub 1, and that's we're going to take the dot product of that in vector n. But I need vector n written in some kind of component form, and I kind of know where I want to be and what variables I want to use at the end of this example. So we're going to say that vector n has the components of a, b, and c. And again, that dot product needs to be 0. Now, I'm going to show you two things with this. We're going to show you how you can move from the vector form for the equation of a plane that involves a normal vector, and just where it comes from through this dot product. Now, we're going to use one of the properties of scalar product and write this as the dot product or scalar product of x, y, and z dotted with vector a, b, c minus vector, so this minus is from all these minuses between as the differences of each of these components, minus vector x sub 1, y sub 1, z sub 1 dotted with vector, our normal vector, has the components of a, b, and c. And I'm running out of room, but all we're going to do now is move this over to the other side with addition. Okay, now, this vector and component form of x, y, and z, that is our arbitrary or general point that's on the plane. And in our diagram, we have that described with a position vector r, dotted with vector a that has the components of a, b, and c. Well, that's what I've labeled as our normal vector or our perpendicular vector. So we have vector r dotted with scalar product with vector n is equal to, now we have another dot product over here, but x sub 1, y sub 1, z sub 1 are the constants, the components that we have, the coordinate, each of the coordinates of our initial points. These are going to be known values, and we're also going to have the known values of our normal vectors. So this dot product is just going to come out to be a constant. But we're going to go ahead and write, even though it is ultimately going to be a constant, we're going to write this as vector a, the component vector for our known point, dotted with vector n. And this is what we're after. This is the equation of a plane. It's another vector form, but it uses the normal vector or perpendicular. So now you have 4 equations for writing, 4 forms for writing the equation of a plane. What's cool about this is if I go off on a different tangent, I want you to see, before we just start, I don't like giving formulas and just say, plug these numbers in and it works, and you have like a 6-minute video, but you don't really understand what's going on. If I leave this in this format and do the dot product here, we're going to have a times x minus x sub 1 plus, that's going to be the product of the components along the x-axis, plus b times y minus y sub 1, the components along the y-axis, plus c times z minus z sub 1 is equal to 0. Now, we're going to distribute this, giving us ax minus a times x sub 1, plus by minus b times b sub 1, plus c times z minus c times z sub 1 equals 0. And again, a, b, and c are the horizontal, well, the components along the x, y, and z axis of the normal vector, known quantities, x sub 1, y sub 1, b sub 1. So these terms are going to be constants. Let's go ahead and move those over to the other side. The right side of our equation, ax plus by plus cz is equal to a x sub 1 plus b y sub 1 plus c z sub 1. And again, we know all of these values, so we're going to get a constant out of this product and get ax plus by plus cz is equal to d. And as you're about to see with our first example, where you might argue, maybe there's a choice, but honestly, I'm not sure what that would be. When we're given an equation of a plane in Cartesian form, if we see that relationship between the Cartesian form of a plane and the normal vector form equation of the plane, the d is some kind of constant from the scalar product of vector A times vector n, but if we can pull apart and realize that this is just the process of going through a dot product, we can pull apart the vector of x, y, z and the vector of ABC and get a vector which is perpendicular to the plane that this is describing, and that's really useful. First example coming up right now. We're going to find the Cartesian equation of plane pi containing the points of A, which has a coordinate of 6, 2, 1, and coordinate B, which has a coordinates of 3, negative 1, 1, and is perpendicular to the plane x plus 2y minus z minus 6 is equal to 0. Now, if you do not have the full understanding and knowledge of this vector form of the equation of a plane which uses a normal vector, good luck trying to get from Cartesian form of a plane through the parametric form. I don't know how you would split that apart and get into maybe this general form for the vector equation of a plane, in vector form. So yeah, when I saw this, I taught IB for the first time last year, and I did really, ultimately, I mean, after a lot of practice and a lot of looking at solutions through the textbook and the released IB exams, I felt like I was getting pretty good with vectors. Even though I taught for 22 years, I had very little experience with vectors, especially in 3-space. And I got to this question, and I had no idea. So let's try and figure this out together. You don't need to do geometry or draw a picture for this, but for purpose of the explanation of the video, and it just helps me kind of see what's going on, I'm going to do a quick sketch. We have some plane, pi, and it has this equation to it. And then there's going to be another plane that I want to find the equation of that's perpendicular to this plane. Intersection line here. And looking at this here, right, our original form for the vector, our first vector form for the equation of a plane is based off of two non-collinear vectors. So this vector, or this plane, x plus 2y minus z minus 6 is equal to 0, you might go, well, all right, well, there's a couple of vectors in here, like maybe vector u and vector v, that if I could do the cross product of, I could find a vector which is orthogonal, a normal vector. And with some of your, some of these questions dealing with vectors and equations of planes, you might have a couple of directional vectors in a given plane that you can find the cross product of to find that orthogonal vector, which is going to be, in this case, vector u crossed with vector v, which again is that normal vector. But I'm only given the equation of plane pi, and I don't have from this an easy way, at least that I know yet, of identifying a couple of vectors that would be in this plane. I guess you could, I don't know, start playing with some numbers and trying to find the 3 points that are in this plane. But if you just realize that, hey, the equation of a plane that deals with a normal vector, it's really easy. I just showed you how to go from this form for the equation of a plane using the normal vector into Cartesian form. This constant is a result of vector A dotted with vector v, the position vector of your initial point dotted with your scalar product with your perpendicular vector. So this right here, this is the result of doing vector r, which is x, y, z, is describing the coordinate x, y, z, and vector n, which has the components of a, b, c. This is x, y, z, the scalar product of that, the dot product, with the coefficients of 1, 2, and negative 1. And then we can move this 6 over to the other side. There's your normal vector right there. You can pull a normal vector right out of the Cartesian equation for a plane. So this normal vector, we don't need to find the cross product or do a cross product to find a vector perpendicular to the given plane. And we want the equation of a perpendicular plane. Well, we're halfway there already. Now I'm going to label this as vector n a normal vector, but it's not normal to the equation of the plane we're about to find. It's normal to the, maybe I should keep it in white then. It's normal to our given plane. And now to finish this up, you can really use either you can think of using the equation here, vector r dotted with vector n is equal to vector a times dot vector n, or kind of fall back to our original vector form of this equation, which is what we looked at in the last video. And when you want to write the equation of a plane, just like the equation of a line way back, you need a point and basically a gradient or a slope. Well, we have one gradient for the plane we're about to write the equation of. We just need another one, so we have those 3 points, the one initial and two terminal points to define the direction of this plane. And we're going to do that by remembering the fact that we have 2 points in this orange plane. Maybe I should highlight it with orange. Now where they are, really this is not drawn to scale, but in this plane somewhere there is a point A and a point B. So if I find vector either AB or BA, I'm going to have another non-collinear vector in the plane for which I want to find the equation. So vector AB is going to be, well, if I do AB, I'm going to have a bunch of negatives. What do I do BA? So terminal minus initial point, 6 minus 3 is 3. 2 minus negative 1 is 3. And 1 minus 1 is equal to 0. So now I have a vector BA that's in the plane which we want to find the equation of. I have vector n, which is, it's not a normal vector to, not a perpendicular vector to the equation of the plane we're about to find, just perpendicular to the one given. And now I want the equation of a plane. Now I have a couple of ways of doing this. So I can look at this and fill out this formula and go through that initial, that vector form of an equation, the equation of a plane in vector form that we learned in the last video. Write that out and then go through a process, convert this into parametric form, and then solve that system of equations or work with that system of 3 equations and eliminate the parameters of alpha and beta and ultimately get to that Cartesian format. Or I can do this. We can actually work with this new format that we were just given, which is these 2 vectors are in this plane, and let's find the cross product of these 2 vectors to basically find another orthogonal vector. So we're going to have to have a little problem with this n here. So we're going to do 3, 3, 0 crossed with 1, 2, negative 1. And to do that, we're going to write a 3 by 3 matrix, vector I, vector j, and vector k, with 3, 3, 0, 1, 2, negative 1, and take the determinant of this 3 by 3 matrix to come up with the components of our vector, which is going to be the cross product of these 2, BA and vector n. So the determinant of taking out the row and column with the I, 3, 0, 2, negative 1, minus the determinant of the 2, oh, we need the I there, minus the determinant that we get when we take out the column and row that has vector j, so 3, 1, going down, 0, negative 1, times vector j, plus the determinant, and I'm getting sloppy, so I'm actually going to just stop this video and erase this stuff and clean this up. Okay, don't love that our diagram is done or gone, but we can now read what we're doing. The determinant of this 2 by 2 matrix, we have 3 times negative 1 is 3, minus 2 times 0, which is 0, minus, we got 3 times negative 1 is negative 3, again minus 0, and that's going to be our component for vector j, component along the y-axis, plus the determinant of this 2 by 2 matrix, 6 minus 3, times vector k, and we get, writing this as a component vector in column form, 3, 3, 3. Just I want to double check that. -3. Okay, there's an error somewhere. Oh, 3 times -1 is -3. Okay, that's why I pre-write all my notes. All right, so using now this vector, which is normal to the perpendicular plane that we're trying to find. And by the way, you don't have to work with this as -3, 3, and 3 because you can just change the magnitude of this vector with a scalar. We could also say that this normal vector, this new normal vector, is -1, 1, and 1. Remembering now, we're going to use that vector r dotted with the normal vector is equal to vector A, a position vector for a known point in the plane. Again, scalar product with the normal vector. We can pick either one of these 2 points. It doesn't matter. It should work, not should, it's going to work out to be the same, but we have x, y, z. Vector r is again your position vector for any point that lies on the plane, any random, not random, but any point in the plane, so that's where your x, y, z comes from. Dotted with now -1, 1, and 1. We're going to use the coordinate A as our known point in the plane, just because I already have component, or this vector A written. That dotted with, that 6, 2, 1 dotted with our normal vector, which is -1, 1, and 1. And we have -x, because you're multiplying, right? You're doing basically what? X sub 1 times, well, you're multiplying the components along the x-axis, the y-axis, the z-axis, and then you're going to add those up. And over here we have 6 times -1 is -6, plus 2 times 1, which is 2, plus 1 times 1, which is 1. And we have -x plus y plus z is equal to -3, or x minus y minus z, which is equal to +3. And that, I've had to erase my diagram to have some room to write out the process of doing this cross product, but it is in orange, and that is the equation of that plane, which is perpendicular to the given plane, of x plus 2y minus z minus 6 equals 0, knowing that our perpendicular plane had the coordinates of A and B. Our second example coming up right now. Bam! We're going to find the vector and Cartesian form of the plane alpha if it contains the lines 2 minus x equals y minus 1 equals 2x, which hopefully recognize this as being in Cartesian form, and x is equal to 3 minus t, y is equal to 2 plus 3t, and z is equal to t. This is another equation of a line, but the difference between the green and the yellow is in parametric form. And we do want to, this is almost kind of like a hint or a tip of how to do the problem. Instead of giving you both lines in Cartesian form, giving you one in parametric form is kind of giving you a hint as to what direction you want to go into, so that you can find enough information about plane alpha to be able to write the equation of it. And it doesn't look like it with the Cartesian form, but especially here with our original, again, vector form for the equation of a plane, you have to have an initial point or a known point on the plane and a gradient. And in a plane, you need basically 2 gradients instead of just one like a line. We're going to find the direction, basically a direction vector for each of these lines, and we're going to do that through remembering, how do you go to Cartesian form for the equation of a line? You go through the parametric form, and you get these equations all equal to, you find little equations for using x, y, and z for lambda or beta, or in this case t. And once you have t is equal to something in terms of z, which we already have, we're going to have t is equal to something in terms of y, t is equal to something in terms of z. we're going to be able to see the connection between the Cartesian and parametric form for equations of a line. So let's do this. We have x minus 3 equals negative t, given us t is equal to x minus 3 over negative 1. We have y minus 2 is equal to 3t, divide both sides by 3, and we have t is equal to y minus 2 over 3, and here we just simply have t is equal to z minus 0 over 1. It's a little bit close there, sorry about that. And I want to look at these three little equations in this format before we write it together as a, and we're not going to necessarily, I don't care about writing the equation of this line in Cartesian format, but I want you to remember that when you have these all set up for lambda, or in this case t, or beta, or whatever the scalar multiple it is that you're, that parameter for your parametric equations you're trying to eliminate to go into the Cartesian form, you can see in here a point that this line goes through, and then the direction from that. You can even kind of see it here. I'm just trying to give you some different ways of looking at this. Your new x is starting from some initial point of 3 and then moving to the left, if you will, some multiple of t, and of course, t is negative, but and then you have an initial y coordinate of 2, and then you're moving some multiple of 3, or maybe say to the right, or towards the positive direction of the y-axis, if you will, at least if t is positive, and then you have some, what's your initial value for z? You know, what's the x-coordinate of your known point for z? That you're going to find some new point, x, y, z, from some initial point. Well, that's going to be 0 because there's no plus or minus here. And then some multiple of, on your parameter of t, which is 1. So whether it's here or whether it's here, we can pull from the yellow line that we have the coordinate of some initial, we'll describe this as a position vector, some known point A, which is 3, 2, and 0. We can see this here, 3, 2, and 0. I didn't have to actually kind of isolate your parametric parameter here. But I think hopefully that'll help for you to see that we have some kind of direction vector, which I'm going to call u. Where are you moving on this line? Where are you moving from your initial point of 3, 2, 0? Well, you're moving in the direction of this vector, which is going to be negative 1, 3, and 1. Now let's repeat the same process for the green line. We're going to have 2 minus x is equal to some kind of lambda. I'm going to use this because earlier in our textbook for parametric equations we just use lambda as our scalar, or parameter for parametric equations. We have y minus 1 is equal to some kind of lambda, and we have 2, oh, miscopied this, z is equal to some kind of lambda. I want to write this as x minus 2. To be able to do that, I'm going to have to divide both sides by negative 1. This is good because we have our y here first is our first term and our coefficient is 1, so that y minus 1 is lambda. I'm happy with that. And here we're really close to what we want, but instead of showing this as a coefficient of 2, I want to show this as division, so we have a direction vector. So I'm going to rewrite this as z with a coefficient of 1 over 1/2 is equal to lambda, and I'm not sure if this is, I don't know if you need all this or not, but we're going to get each of these equal to lambda, just like it was over here with our yellow line. And we have x minus 2 over negative 1 equals lambda. We have y minus 1 over 1 is equal to lambda. So I'm going to just trying to really make it obvious where we're going to find those initial points and the components of our direction vector for this line. And we're going to have z minus 0 over 1/2 is equal to lambda. So for the green line, we have a known point that it goes through, which is 2, 1, and 0. We're changing the signs as we pull these out. And we'll call this, maybe this known point, describe it with a vector b, or we could describe it as a coordinate, of course as well. We'll say that. So this line has a known point of 2, 1, and 0, and it has a direction vector, which we'll call v, of -1, 1, and 1/2. Now for the rest of this problem, I don't want to work with a fraction, so I'm just going to apply a scalar multiple to this. It's just a direction vector. Its magnitude is not important. We're going to multiply this by 2 and say that this is 2 times vector v is, I'm not going to necessarily use that label, but -2, 2, and 1. So this is the information we're going to use for the rest of the problem, and I don't want to carry a mistake through that if I've made some kind of silly error. We have some plane that has this yellow line in it. We have, and I'm going to write, I'm going to identify this as basically like this, a direction vector. So we have a plane with a line in it, but we're going to pay attention to, let's say, this particular point. So we have the point of A, which was on the line, but I'm not going to focus on the whole line. This point A, which is 3, 2, 0, and this direction vector. And then both of these lines fall or within the same plane, so I don't need 2 position points. I just need 1 known point in the plane. But from this green line, what I'm going to pull out is the fact that we have another non-collinear vector. So we have 2 non-collinear direction vectors, basically, that are parallel. Potentially, they could just be simply parallel, but they're actually in this plane of v. Well, you realize now we have enough information to write the equation of our plane, whether we want to write it in this format, which is just sort of our standard initial equation of a plane which we learned, and this one that we're exploring in this video, which is using the normal vector. Now, if we're going to talk about using the second form of this equation, which is going to use a normal vector, we need to find the cross product between these 2 directional vectors. So I'm going to clean all this up. I'm going to write the fact that we have a known point on this plane, and I'm going to write out vector u and vector v, and just basically go through the same process we just did in our last example. So it's a fair amount of work. You saw me doing setting up the 3x3 matrix, going through the process, finding the determinant of that, and breaking it down to those 3 2x2 matrices. We got that cross product, and then we say that vector r dotted with, or the scalar product of vector r with vector n, our perpendicular vector, is equal to component position format vector for some coordinate that's on the plane. I could have used the other coordinate, which I guess I have erased. Well, yeah, it was in my work. But we went ahead and decided to use 3, 2, 0, and then take the scalar product of that vector n, and we got x minus y is plus 4z is equal to 1. By the way, these signs are the opposite of what they were in my work, because in my work, my second row for that 3x3 matrix was -2, 2, 1, where here I had my third row as -2, 2, 1. I still got the same answer. Actually, in my solutions, what I'd initially got was simply -x plus y minus 4z equals -1, and then you can just multiply the entire equation through by -1 and get the same answer. So as you do the cross product, yes, the order of which you do the cross product, because the cross product of vector u and vector v is the opposite as the cross product of vector v crossed with vector u, it does make a difference in the sign. But in examples like this, where you're coming down to the Cartesian form for the equation of a plane, it works out fine, and you get the same answer either way. Now, You can also get to that final answer by writing the equation of this plane not using the normal vector, but just using that initial that vector form that we learned that does not use a perpendicular vector. And that is going to be that vector r is equal to vector a, the position vector for coordinate a, which is 3, 2, 0, plus alpha times one of the direction vectors, so negative 1, 3, and 1, plus beta times the other directional vector, negative 2, 2, and 1. Write this out in parametric form. Now remembering that this is a position vector for any general point that's on the plane. And we get x is equal to 3 minus alpha minus 2 beta. Y is equal to 2 plus 3 alpha. Hope you appreciate the alternative forms for doing the same problem. Z is equal to the initial point of 0 plus alpha plus beta. Okay, so what we're going to do is we're going to add these equations, and let's get rid of the parameter alpha first. So we're going to take this first equation and multiply it by 3, giving us 3x is equal to 9 minus 3 alpha minus 6 beta. Yes, and now we're going to add this. Basically, we're doing 3 times row 1 plus row 2 and getting the equation of 3x plus y is equal to 9 plus 2, which is 11. The negative 3 alpha and the positive 3 alpha are going to cancel out. We have negative 6 plus 2, which is negative 4 beta. And with our second and third equation, we're going to have to multiply z by negative 3. We don't have to, but that's going to be the easiest thing to do. Negative 3z is equal to 0 minus 3 alpha minus 3 beta. We're going to add those up. Basically, we're doing row 2 minus 3 times row 3. And that is going to be y minus 3z is equal to, the 3 minus 3 are going to cancel out. 2 minus 3 is negative. Getting quiet because it's easy to make mistakes when you have all this work. Now we're going to take those two equations, and I'm just going to write it, well, actually, let's do this. I'm going to rewrite these, but we want the betas to cancel out. So if this is a negative 4, I want this to be positive 4. I'm going to multiply this equation as I move it over here to have some room by negative 4 to create a coefficient of positive 4 in front of that beta. We're in this pretty advanced math here, and yet we're still solving equations basically by linear combination. Pretty cool. All those skills we learned are still getting used. We got our opposite coefficients in front of beta. Let's go ahead and add these up. We have 3x. We've got positive 1y minus 4y is negative 3y. Looks like this is coming out to be different, but it won't. Plus 12z is equal to 11 minus 8, which is 3. These are canceling out. And these coefficients are larger, but if I come through here and I multiply this Cartesian form of our plane by 1/3, we get the same answers we had before as x minus y plus 4z is equal to 1. Double check just to make sure. And so there you go. If you find this to be pretty straightforward, maybe you want to go from our original vector form for the equation of a plane to Cartesian form, or you can go through that cross product using and the dot product using the equation for the equation of a plane that uses a normal vector. Got one more example coming up right now. Bam! We are going to find the Cartesian equation of the plane alpha if it contains the point negative 2, 1, 3, and the line, which is given to us in Cartesian form of x minus 3 equals y plus 1 over 3, which is equal to z. What do you need to write the equation of a line? What do you need to write the equation of a plane? Well, whether you're going to go into Cartesian form or not, you need a point on the plane, whether you're going to use this form or this form for the equation of a plane in vector format. You need a point on the plane described with this position vector, and you need some kind of gradient, whether that gradient is two vectors, the sum of two vectors which are parallel to the plane, or you're using a vector which is orthogonal. We're going to do the orthogonal one in this video since we just got done doing, well, we used both methods in our last example, but I focused on the one where we used the parallel vectors, or we used the first form. So we're going to write this, we're going to break this apart into, from Cartesian into the three parametric forms, or that combination of those three parametric equations making up or describing this line. So we have x minus 3 is equal to lambda. We have y plus 1 over 3 is equal to lambda. And we have that z is equal to lambda. And just to make this really, really clear, we're going to make each one of these look identical so we can clearly see what at least one point, we can find one point along this line very, very easily, and then find a direction vector or sort of a gradient for that line. So we're going to write this as x minus 3 over 1. We got this already, really good. Y plus 1 over 3, again, is equal to lambda. And here we're going to write that z minus 0 over 1 is equal to lambda. So we can see that the line that they gave us has a point, let's just call it A, which has the coordinates of 3, negative 1, 0, and a directional vector, a gradient, if you will, for this line is in the denominator. Or we can see it, actually, I could have done that. I could have multiplied this by 3 and then subtracted 1. I'll show you that as well. I'll just do it out here. X is equal to 3 plus lambda. Coming down here, multiplying by 3 and subtracting by 1, we have y is equal to negative 1 plus 3 lambda. And we have z is equal to 0 plus lambda. So however you look at it, whether it's moving in towards writing this in this middle step of going into our parametric equations, or just solving each of these for x, y, and z, which honestly is better now that I'm saying this, but we can see that point again of 3, negative 1, 0 here, and lambda is that scalar multiple of our gradient or directional vector, which is going to be 1, 3, and 1. So now we know a point and a direction. Okay, so it gave me a second to check my answer while my wonderful wife was answering the phone. We now know for this plane alpha, one point that is on the plane, and we have this other point which is also in the plane because the plane contains the line, and we have a direction vector. Well, whether we're going to use a normal vector or equation or the just regular sort of vector form for the equation of a plane, we need two non-collinear vectors. And right now we only have one sort of gradient or directional vector for our plane, so we need another one. Well, we have that. We have 2 points that are in the plane. So we can find vector AP, which is going to be terminal minus initial, negative 2 minus 3, 1 minus negative 1, and 3 minus 0. And so we have vector AP is equal to negative 5, 2, and 3. So we have a point, and we have two non-collinear sort of directional vectors that are together the gradient of this plane. And these are not scalar multiples of each other, so they're not parallel. Thus, they wouldn't be useful. Now, I just want to make sure that I haven't wrote an incorrect number because I did some mental math incorrectly. Okay, now we're going to find the equation of this plane by going through the normal vectors, which we're going to do the cross product between U and AP, which is going to be found, I'll have the answer up there in a second, by setting up a 3 by 3 matrix. You might have noticed some patterns that you can use to find the cross product vector quicker. I just keep showing this process in case your teacher wants some really like formal work and see that you actually know what's going on, not that you just recognize some pattern and sort of shortcutting this process. But do whatever your teacher is happy with. This is going to be, we want the determinant, this is going to be equal to the determinant of this 3 by 3 matrix. So again, row, column and row that contains the I taken out. That is going to be a coefficient of our I component minus the determinant. Take out the column and row that has again the J, vector J component, plus the determinant of the 2 by 2 matrix when you take out the column and row that has the vector component K. One last time, because this is the last example, work out these little 2 by 2 determinants. We have 9 minus 2, which would be a component for vector I, minus 1 times 3 is 3, minus negative 5. That'll be our component for vector J, plus the determinant of this 2 by 2 matrix, 2 minus negative 15. And that is going to give us a cross product, which is equal to, I'm going to write this in column component form. 9 minus 2 is 7. We've got 3 plus 5, which is 8, but it's got a negative out here, so negative 8. And 2 plus 15 is 17. Double check one more time, just so we're good for the camera. Using that normal vector, we're going to fill in this formula vector R dotted with our normal vector equals some position vector for a known point on the plane, taking that scalar product or dot product with that normal vector. And we have, and we do want this in Cartesian format. So I'm going to go ahead and take the vector R out and replace it with that, the component form of x, just x, y, and z, general point on the plane. Dot it with our normal vector, 7, negative 8, 17. We're going to use coordinate A. You know, we can't do this problem without understanding how to find the point and the direction, the gradient of this line. So it's really kind of not a great idea to use information that you found yourself in your work whenever possible, though if this isn't right, the rest of our work isn't right. But you could use, you know, P here, and I could call this the position vector for coordinate P and have negative 2, 1, and 3. I'm going to dot that with our normal vector of 7, negative 8, and 17. And we get 7x. And by the way, I did not use coordinate P in my notes. I used coordinate A that I pulled from the line, but you'll see that we have the same answer. Negative 2 times 7 is negative 14, plus 1 times negative 8 is negative 8, plus we have 30 and 21 is 51, so we're looking at 7x minus 8y plus 17z is equal to negative 2229. Double check. And I am thankfully done. If you made it to the end, thank you so much for watching all of these examples. I hope you learned something. And I'm Mr. True. Bam! Go do your homework.